So welcome to the Computer Science and ITS Faculty Seminar Series at Marist College. Our speaker today is Parris from IBM. Carl is a senior technical staff member at IBM who's had a lot of experience with large systems design, and in particular his area of expertise is performance. And in more recent assignments he's been involved in looking at other architectures and other chips that might be incorporated into System Z. So Carl's going to take us through an overview and some thoughts on how the cell processor, the cell broadband engine, can coexist with large systems. Carl?
Good, thanks, Angelo. So hopefully I'll be able to keep you awake today, because if you were like me, you stayed up probably past your bedtime last night and watched a little TV. As Angelo mentioned, my background at IBM has been mostly in mainframe performance. And for a number of years in the 90s, I was the mainframe representative from IBM to the TPC Council, which is the Transaction Processing Performance Council. And some of you may know that they defined a series, they defined a number of industry standard benchmarks, performance benchmarks that all the competitors in the industry use to compete against each other. And when I first joined, they had one benchmark called TPCA, which is a very simple debit-credit benchmark. And they decided that was too simple, so they went to a TPCC benchmark, which was a transactional, online transaction relational database benchmark. And I was still very frustrated during my whole time on the council, is that all of these benchmarks were really one operating system running on one box, running one application. And then they would run it to 100%, and they would say, here's how many transactions a second we got, this is how much the box costs. Now you know the transactions per dollar, and that's all you need to know about performance, and so buy our box. And in the meantime, in the mainframe side, we were really dealing with a view of performance that I call operational performance. And these benchmarks did not allow us to show off some of those capabilities. And so we formed another subcommittee to create a benchmark that had online transactions concurrently running with batch applications. And we put some availability scenarios, like how fast can you recover from a failure and things like that, into it. And we defined what I thought was a really great performance benchmark specification, and it was voted down twice by the council. Because at that time most of the vendors were not in a position to run one operating system on one box. Since then, I've really been focused on how to talk about operational performance, and really not just the performance of one thing, but many things running on a system. And now you see in this presentation, I kind of take my background in operational performance and start to look now at heterogeneous systems performance. Please don't hesitate to interrupt me at any time. But I'm going to talk a little bit about the System Z value proposition. And remember, this is a presentation that I give to customers, so it will have a little bit of that, buy me attitude in it. But then I'm going to do a little side trip into processor chip options and balanced design. And you'll wonder, why am I going off on this side trip? But hopefully I'll bring that back together a little later in the presentation. And then what we're looking at in terms of future directions in System Z, in terms of integrating alternative architectures into the System Z ecosystem. Then I'll go into a deeper dive on the cell broadband engine itself, how we got involved from the System Z side and looking at integrating cell into our environment. And then I'll go into how we're going to integrate it in some of the activities there, and then we'll wrap it up.
Carl, could I ask a question?
Mm-hmm.
You mentioned just a little while ago the concept of heterogeneous system performance. Does that mean within the umbrella of System Z with heterogeneous engines, or does that mean really, does that take network delays into account?
It's a little bit of both, actually, as you'll see. I'll talk actually in a few charts. I'll talk about how I want to scope that discussion. So when someone says, well, what's unique about System Z from the other servers that are out there, from my performance background, what I like to emphasize is the fact that we have this large shared resource pool, and that we're able to run a lot of things in that shared resource pool, and we're able to prioritize some things versus other things. We're able to virtualize the resources, and that all those technologies together are really what makes System Z unique from the other systems out in the industry. So this is a marketing chart. I wouldn't know how to make that graphic on the left. But this next chart is my chart. And so in the late 90s, I did something called, I put together a demonstration of the mainframe operational performance capability that we called the metal test. In other words, we showed the metal of the platform. And I did it again around 2003 or 4, and this time we used WebSphere workloads to show off the capability. So, and in fact, there's a whole, I have a whole presentation just on this metal test if you're ever interested. That's really good to understand the basic capabilities of System Z. So what we have here in the test, and we did this live and with gauges hooked up to the system, so you could see as we went through these various different scenarios, you could look at gauges and look at the transaction rate, look at the CPU utilization for each of the workloads, look at the CPU utilization across each of the LPARs. But what we had, we did this on a Z900, so this is a few generations old now. We had 16 physical CPUs down here. And on top of this 16-way SMP server, we had 5 logical partitions, each with their own operating system instance, in this case, all ZOS. And we have the ability with our PRISM technology to define 16 logical processors in each of these 5 logical partitions that are all sharing these 16 physical processors underneath. So in these 5 partitions, in systems A, B, and C, we ran a workload where we took one of our KICS-DB2 performance benchmarks that simulates an order entry kind of environment. In fact, it is the TPCC benchmark with a lot of modifications in it. And we put a WebSphere front end on it. So we now had WebSphere on ZOS driving KICS-DB2 transactions. And system A, B, and C were all sharing down here one copy of DB2 data on ZOS. So these were configured as a parallel sysplex. So we had a sysplex in a box. And work was being sprayed to each of these. And so in the main part of the workload, we had 7 online transactions that we called the order entry transactions. And we gave them a workload management priority or importance rating of 1. And then we had, in red here, we had another transaction called the order analysis transaction, which was very, very CPU intensive. In fact, what it did is it did a simple read of the database, and just to chew up CPU cycles, it calculated the value of pi to 17 digits of accuracy. But the idea was we wanted to introduce a transaction into this mix of online transactions that would try to grab all the CPU cycles. So we used Workload Manager, which is designed in the mainline path of WebSphere on ZOS, to basically make sure that the priority for CPU-intensive the order analysis transaction, didn't steal all the cycles from the high priority order entry transactions. So here we had Workload Manager within WebSphere subsystem. We also have Workload Manager within DB2 that does that for store procedures, for instance. Over here we had another production workload for this pretend company. It's the trade benchmark. It was WebSphere driving DB2 transactions. And then here we had, in system E, we had a partition that we said is a test partition. So here we had some DB2 batch, had no WebSphere in it at all, at priority 4. And then we had this test version of this trade benchmark running here. So here we used Workload Manager within a single instance of ZOS to distinguish between these 2 different workloads, which were at different priorities. And then across all 5 partitions, we had Workload Manager interacting with something called IRD, or Intelligence Resource Director, so that we were now able to balance the resources not just within an OS or within a sysplex, but across all the partitions of this sysplex, based on the priority of workloads in one partition maybe needing to steal cycles from a lower priority piece of work in another partition. So in addition to that, we had Sysplex Distributor, which is really a software router that runs on ZOS, that for these 3 partitions in the sysplex right here was routing work to the least busy of these 3 partitions based on real-time feedback from Workload Manager. So we have this top to bottom, from the router distributing work to the resources, to here, WLM distributing resources to the work, this top to bottom integration of really virtualization and resource management. And to have a system like this, you really have, it influences how you design your chip, how you design your firmware, and then your middleware and your operating systems and so forth. So that's really, from my perspective, kind of from a technical perspective looking up, what it means to have a large shared resource pool. So now I'll do this little side trip into processor design options. And I'm going to use a period in history in which the contrast between these two techniques, or some of these different options, were the most apparent. And I would say that history has changed, that things have changed since then. So these are older. This is an older comparison. But at the time that I did this, the Power 4 chip and the Z990 chip were out in the market at the same time. These are both, I guess, 2 generations old now. And as a chip designer for a microprocessor, you get basically so many transistors to fit on a piece of real estate, and it's up to you how you use those transistors. And you have various constraints. You can only have so much power that goes into the chip and things like that. And so you will see different chip designers make different trade-offs. So the power guys took their real estate and they used most of the real estate on their microprocessor chip for the processor circuitry itself. So they had a 4-pipe superscalar design, out of order, very sophisticated, a lot of floating point registers. They used very, very little circuitry for RAS, that's things like error detection and correction and things like that. And then they had a modest-sized cache. Over on the Z990 side, we used a lot of our real estate for RAS. So we actually have circuitry in there that will execute the same instruction twice to do a compare. If there's a difference, we'll know that there's a bit's been flipped by some atomic radiation in the air, photons flying through the air or whatever, so that we have very sophisticated soft error detection. And that takes up some transistors and some real estate. We have the processor, modest amount of space for the processor, and then we have this really big cache. And you look at this and you go, what were the guys thinking down the road here? Because if you run the spec-int benchmark, which is what one of the benchmarks used to design the power chip, you would go, well, the spec-int benchmark doesn't have a very big memory footprint. That's that little green ball up there. You don't need that big a cache, and we've way over-designed our cache here. But the spec-int benchmark is one thread or one user running one application on one operating system at a time. So it's designed really to test the speed of the main core of the processor and the compiler technology, but it's not good for looking at operational performance.
Carl,
Yeah.
one other question. I'm sorry. On the Brown side, the Power 4 side, minimum RAS is not penalized. I don't know what that means.
It's not.
Penalized?
Oh.
I just don't know what.
This was basically saying for this benchmark. You can
Oh,
have
I
no
see what
RAS
you said.
and running the
You
spec-int benchmark. I say, hey, look
It
how
doesn't
fast
have-
I am,
okay.
That's right.
and
Okay.
you haven't demonstrated the value of the RAS circuitry there.
Got it.
So here is the same 2 chips running the TPCC benchmark, which was the other key benchmark used to design Power 4, and Power 4 published industry-leading spec-int and TPC numbers, and you can be sure they designed that cache to be just big enough for the main working set of the TPCC benchmark. And again, it looks like we're off base over here on the Z side. Now what happens if you decide you're going to run multiple operating system instances on a server, or you've got a workload with a very big memory footprint, and now you see that in the Power 4 days, that was it was before they had their p-hype virtualization. This became a problem. So while this processor was very fast, it was spending a lot of time waiting to get data from memory because it kept missing the cache. Meantime, over here, we've been running Prism and virtualization and multiple LPARs on Z for most of my career, actually. And now the reason for this large memory nest becomes a little more apparent with this focus on, again, the large shared resource pool design point and operational performance. Now, in all fairness, Power 6 now has p-hype. The Intel x86-based vendors have VMware, and they've all learned, and you'll see a few charts later, that they're now dedicating much more of their real estate to cache because they need to do that in these multi-operating system environments. And in our case, we now have 4 processor cores on a chip. We've scaled back a little bit on the cache, trying to maintain, again, our design point for operational performance and virtualization, but we've made a few trade-offs also. So in terms of System Z future directions, and I hope this helps with your question, the question is, okay, now we're talking about adding accelerators to this large shared resource pool, how do we do that? Or what does that really mean? And what do we mean by acceleration? So now we've got a Z system that's got some function in it, and that function is compute intensive, but it's very predictable. We know what the inputs are, we know what the outputs are, and we just do the same thing on that piece of data every single time. And so what we then, when we identify those kinds of functions, we will actually put them on the silicon, on the chip, and we'll accelerate them right in the processor itself. And we've done that with things like encryption and compression. So we've integrated accelerator technology for now many years on System Z. Now there's another kind of acceleration that I would say is acceleration in quotes that we've been talking about on System Z, where we take a function and now we say you're going to run that function in System Z right on the processors, but we're only going to allow you to run that particular function on a subset of our resources. And because you only run it on a subset of those resources, we won't charge you as much for the software and for the hardware. And so we've been calling it acceleration, but really what we're doing is we're accelerating the price performance part of the equation, or the price part of the equation. So we've done that with IFLs for Linux engines, ZAPs for Java, and ZIPs for various kinds of DB2 processing. And I'm not sure if you're all aware of some of these things or not, but if they're not, these aren't familiar concepts, let me know. We can talk more about that, if not now, at another time. But this is more for a price performance discussion. But then we have alternative systems now that just do things that we didn't design Z to do. And as I'll talk about in a few more minutes, we expect to see more and more of these kinds of alternative systems appear in the marketplace. And so now what we want to do is we want to integrate these alternative systems into our enterprise system environment in various ways, but they will still be distinct and separate from the main Z box itself. And so what we're doing is we're doing now that with cell processors, data power, which is used for XML, XSLT web services processing, and we're also looking at some stuff in the data warehouse acceleration space, which I don't have on this chart. So these are all based on non-Z technologies. So is that?
That helps.
Okay.
Yep.
So now let me do a deep dive into one of these alternative systems, the cell processor. And then again a little background, and I think it's probably fairly familiar information now, but if you look at the increase in clock speed, that's a logarithmic chart on the left. Over time, we've been spoiled by this more than linear increase in clock speeds. And in fact, had we continued on the trajectory we've been on for over a decade, we now would have 10 gigahertz laptops. We don't. And there are reasons for that. This is attempts to discuss a little bit of it. Don't ask me too many questions about the physics of it. But basically over here what this shows is that when we try to increase the clock speed on a microprocessor chip by close to 50%, we need to increase the amount of power we pump into that chip by almost 3x. So we are at a point now where we're pumping in about 200 amps or so into a small microprocessor chip, about the amount of amperage you have in your household into a small chip. And that starts to really create a number of problems. So one of the reasons that the way we go faster is by shortening or narrowing the width of the gates. So here we've got gate length decreasing as we go from left to right, and we're now down to gates that are maybe 4 or 5 atoms in thickness. And one of my colleagues like to say, when you get down to less than 1 atom, you start having problems. But basically what happens is, as these gates get narrower and narrower, we can't control the behavior of all the electrons and make sure they stay where they're supposed to be, and they start jumping the gates, and that's called leakage. And so what happens is, when you plug your system in, where you expect to have it not consuming too much power because it's really not doing anything, we're already jumping electrons. And so the passive power starts to cross the active power line before you've actually even started to do any work. In addition to that, besides the power you're pumping into this thing, you now got to expend a lot of power cooling it. And you even have problems now with the speed of the fans exceeding OSHA limits in terms of the noise and so forth. And so all these things combined are really limiting the options that microprocessor designers have. So Moore's law is not dead. Moore's law basically says that every few years we can more or less double the number of transistors on a chip, so we're still able to shrink the number of transistors on a chip, but what we can't do is drive the frequency up. So there are some technologies out there in the semiconductor field that will help this, but none of them really will fundamentally change this problem and this limitation that's hitting the whole industry, not just IBM. And so what's happening is people are starting to say, I've got so many transistors I can put on my chip, how am I going to use them? And before they kind of did the same thing they did in the previous generation, because they just kind of modified the chip a little bit to handle faster clock speeds, maybe threw in a few little swizzles here and there. But now they're looking at very dramatically different designs, and you see all kinds of things that, different kinds of chips that are coming out, particularly in the multi-core space and the multi-threaded space, and then also in the vectorization space. So what we're seeing is basically that one size chip or one kind of microprocessor design will not satisfy the full spectrum of computational requirements, and that you're going to start to see multiple chips out there doing different things. And at the same time, what we're seeing is that once you had high-performance computing over in that corner, and you had your transactional commercial processing over here in this corner, and they were very independent and separate from each other, we're now starting to see those two worlds combine. And so the requirement, we believe, to put these different kinds of technologies together will increase dramatically over the next few years. So it's with that background in mind that IBM had a secret project with Sony, Toshiba, and IBM. And they invested close to $500 million over a 5-year period. And in 2005, we came out public for the first time with the first technical disclosures on the Cell Broadband Engine processor. That alliance has been renewed for another 5 years. And so let me tell you a little bit more about the processor. So here's the Cell chip microprocessor right here. So if you look at it, I don't have a way to point, but that upper left-hand box is a power processor. We call it the PPE, the power processing element. And it's a full function power processor chip. It runs a Linux operating system, and you can think of it as a general purpose processor core, so it's one core. Then you've got 8 cores here called SPEs, or synergistic processing elements. And each of these cores is essentially a vector processor in and of itself. So it's got a vector register that's 128 sections wide. Each section is 128 bits. There's an instruction set architecture that allows you to manipulate these vector registers. What's interesting about it is it does not run an operating system. It only runs user code. So the PPE will basically functions as a controller, distributing work to one or more SPEs on the chip. The user code runs here, and these little brown areas here are the local cache, although actually what we call it is a local store, because it's up to the user program as to whether they use this as a cache or not. So it's really a workspace. It's a local store that the application can use any way they want. And one of the advantages of this is that because you have no operating system here, you don't get interrupts, you don't get somebody else to say, I need something that you've got, you don't get locking and serialization. So you put something on here, it will run with the same performance. It's very deterministic every single time. So you've got these 8 cores doing these vector processing work, and then what you have is a very fast internal bus between all of the cores and the processor, all of the SPEs and the power processing element. You have the ability to do direct memory access to the power processing element memory. Also, this chip is on a blade, in a blade form factor, so there's actually 2 of these chips on one blade that also share memory that's on the blade. You can have 32 gigabytes of memory on the blade and do direct memory access into that. So we can move memory directly from the memory on the blade into the memory on these SPEs, doing remote direct memory access kinds of things. So you've got this fast internal bus, and then you've got a very fast bus on and off the chip. So when you look at general purpose servers, you expect to see, as I showed you before, a fair amount of real estate for your cache. And the idea is that's kind of a warehouse view. You need something, you go out in the warehouse and look to see whether you've got it, because you put a bunch of stuff in there hoping that somebody actually needs it. this is kind of a just-in-time model which says you get the data onto this chip just before I need it. I'm going to process it and I'm going to get it off. So there's double buffering techniques that are used. And so the idea is that we dedicate most of this chip real estate to processing and not to memory or cache. So to be able to use this, your data does have to be structured in a way that you can kind of stream it on the chip and stream it off the chip, and that's sometimes why you might hear it called, a little simplification, stream processing. So a few other things that I haven't mentioned. It does floating points extremely well. It does integer processing also very well, as well as strings. C++, and Fortran are the languages. We're not running Java natively on this. And there's actually a very interesting capability with security. Because this was developed with Sony, and it was developed for the Sony PlayStation 3, that's the chip that's in the Sony PlayStation 3, they were very interested in being able to secure the code that runs on it, because they run their Blu-ray code on the Sony PlayStation 3. So they can have their Blu-ray code running in an SPE, and they can essentially put a security wall around that, so that no one can get in there and see that code. The PPE can't look at it, all it can do is stop and start it, but it can't get in and see the code. So you also have that security capability. And when this first was designed, or when they first started the design, the target was that this chip should be able to run 100 times faster doing graphics processing than the best general purpose processor of the time. They actually achieved about 50x faster when it finally came out. So any questions on this before I move on?
Is that security feature on any of the SPEs? Or is it
Yes.
one?
Yep. Yep.
So you said that the goal was 100 times, and they actually achieved 50?
50x,
Okay.
yep. Yep. So is everybody here familiar with SIMD techniques? Let me, since there's various backgrounds here, let me just show this a little bit. But when I talk about vector processing, I'm really talking about using SIMD techniques in the program. So here is scalar code over here. And this is what most commercial applications are using, are scalar programming techniques and a scalar instruction set architecture. So here, let's say I want to add 4 pairs of numbers. So now I'm going to do 4 adds, one after the other. So I get an instruction, I bring it into my instruction register, and it says, add one register to another register. Well, let's say add something from memory, put it in a register, take another thing and put it in a register, and then add them together. So I decode it. So then I go and get one number, I go and get another number, put them into a register. Another cycle, I add them together. Another cycle, I put the results away. And then I do the same thing again 4 times. So I've done 4 instruction decodes, 4 executions, 4 putaways, and that's how most commercial applications are written. With a vector architecture, now what I do is I have different kinds of instructions, and my registers are organized differently. So now I can take an instruction that says, read an instruction, decode it, and it says, get 4 numbers and add them to another 4 numbers and put the results away. So I decode one instruction, that's the single instruction. I get 4 numbers and put them into one set of vector registers, another 4 numbers in another, and then in one cycle I add them or compare them or whatever all together or multiply them, and I get my 4 results. So now a single instruction has operated on multiple pieces of data. We refer to this as data parallelism, and overall we call this single instruction multi-data programming, or SIMD. So if I go back to this chip, each of these cores does data parallelism or SIMD processing. So I can get a very significant speed up compared to scalar on one core. Then I've got 8 of these cores on one chip. I've got 2 chips on one blade, so I can actually do this 16 times on one blade. So if I can take advantage of data parallelism and multi-threaded instruction level parallelism, I can get very, very significant speedups. So that's really combining 2 forms of multi-threaded computing. So where is this good for? SPU is the same as SPE. I've never understood the distinction. But basically, ideal codes for those SPE cores are where the data is structured and predictable, where you may be doing multiple operations, but the same operations on each piece of data as it comes through, where you can parallelize it across lots of cores, where you can SIMD-ize the data and the code. So these are compute-intensive codes that fit the streaming model. Generally think anything to do with graphics is very good, but I've highlighted a few things. We've been looking at numerical algorithms like Monte Carlo simulations. Yes? Yeah.
When we attended this workshop last year, we were told that the blades at the time were pretty good, and that was the case for the PlayStation 3, were pretty good for integer arithmetic, but not so much for FP, for floating point. But there was a new release that was coming. Is that what we have today? Or?
Well, the cell processor has always been very good at single precision floating point. Where it was weak in the first few generations was double precision. So in May of this year, we came out with the QS22 cell blade, and we fixed the issue with double precision floating point. Because with the graphics processors, you know, for things like a PlayStation, single precision is fine. You're not worried about so much accuracy. If you lose a little pixel here and there, you don't want, the eye won't see that. But when you start getting into numerical algorithms, particularly for like financial services sector and things like that, the double precision becomes very important. So that's been the QS22 that came out is 2.5 to 5 times faster double precision than maybe what it was that you were talking about at the time.
I want to just go back to something you mentioned before. You were talking about, in one corner there used to be the transactional type processing systems, and the other the highly computational, but they're merging together. Is that merging together in the financial industry? Is that where you really see these types of merged applications or heterogeneous environments being very useful?
That's one of the places that we're seeing them, and that's where I've actually spent most of my time to date. And so it's been an interesting experience because I'm a transaction guy, as a mainframe guy, and now I'm walking into investment bank environments where they're running they were running Monte Carlo simulations. In fact, in a few minutes I'll show you a chart that is now kind of sad, the collateralized debt option calculations we do really well on cell. Those are the CDO things that have gotten the financial markets in trouble. But so they are not mainframe guys in the investment bank, and yet they have these very, very complex systems where they do they have these stock feeds coming in. They are very focused on low latency messages getting into the system. They want to do Monte Carlo-like simulations against these. They want to route them to various systems and try to match different kinds of trades and trade book matching systems. And then they want to commit the trade on which is often on a back-end Z system, maybe running Kix or DB2. And so on one hand, they say, we're not mainframe guys, we just do the high-speed stuff in the investment bank. On the other hand, they're saying, particularly now after what's happened, we need to have a single view of all the risk for all of the different parts of our investment bank and our commercial bank. And we want that all in a centralized area. And it's got to be highly available, and we have to have some governance over it in terms of who can look at what from a security perspective, and we have to be able to do reporting and Sarbanes-Oxley and all that. And so now with the need for compliance and more regulations, they're starting to say these systems are too complex, we need to shrink them down and centralize them and have some form of more unified management. And that's where we start to see what I think will be this merging of commercial and high-performance computing. And I'm not the only one, actually. I kind of was seeing this on my own and bringing this back into the lab in Poughkeepsie. Not too long ago, I presented to a company called Tabor Communications, and they have a whole white paper they've done on Edge HPC, where they're talking also about this merging of kind of, well, you have the traditional HPC, your kind of scientific supercomputing kinds of stuff, and they're seeing that technology kind of growing out of that space and starting to cross a little boundary with the commercial stuff that also has these requirements to do this high-speed computing. We're working with some companies looking at credit card fraud detection, where they use neural network algorithms that lend themselves to SIMD optimization. There's another example that I just had in my mind and it just jumped. Oh, I know. With data analytics, we're starting to see the ability to do very high-speed queries where we use SIMD techniques essentially to load data that's been structured in a certain way into the vector register, compare everything all at once. And so we're starting to see the opportunities to use this kind of architecture also in the data query space. So here's back to a little chip real estate. So Power 6 processor on the upper left, but if I focus on Intel for a moment up top, when we first did this chart, Intel was out with their dual core 65 nanometer, but here you can see about half that chip, or even a little more than half, is now is dedicated to cache for these two cores. Now they shrunk that down to 45 nanometers with a quad core, and what you see here is, you see this black line in the middle. What you have now are two cores above the black line and two cores below, so it's really two chips sandwiched together. So what you now have is what they call a dual chip module to get the quad core. On Z we actually have 4 cores on one chip now. But here you again see a lot of the real estate for cache, and then down here you've got the cell. It's a smaller chip, mostly dedicated to computational capabilities, and these are theoretical max ratings, but for single precision they are just under 100 gigaflops. This is about 230 gigaflops. They're using about 130 watts to 75 to 95 watts. So cell is basically saying that they have a superior throughput per watt capability. And of course the competition is now on as to, from generation to generation, can they keep that edge? So if you look at kind of the taxonomy of different processors that are out there, what we do is we kind of compare the scope of purpose of a microprocessor design to the efficiency at implementing a specific task. So over here you've got your general purpose processors, broad scope of purpose but not as efficient. And then as you work your way over here to the extreme, you have your digital signal processors, FPGAs, graphics processing units. ClearSpeed is mostly a floating point mathematics chip that's on a card you can plug into a PCIe slot. And then when Cell first came out, Cell was all by itself kind of in this space here, trying to stake out a high-performance computing part of this taxonomy. And now that people have seen what Cell is doing, you start to see GPU vendors like NVIDIA and ATI saying, gee, we should go after that commercial HPC space. And they're trying to get into the financial markets. Intel is coming out with a chip called Larrabee that's going to go very much after the Cell space. And then here you have people like Apple and AMD who want to combine on PCIe cards with GPUs in it, plugged right into their workstations or servers where they had a CPU and a GPU combined in an integrated package. So I'm going to come back to a variation on this chart a little bit later in the presentation. So here's a little seeing is believing, so a few little demos. The thing that made the news this summer was IBM has been working with Los Alamos Laboratory, where they've packaged up cell processors with AMD processors in what they call a single tri-blade. So they actually have multiple blades packaged together. And by putting these things together, they've built a supercomputer that now has achieved 1.3 petaflops, or 1,330 teraflops. Using, again, it's a heterogeneous environment, so the AMD processors in this case are the host, and the cell processors are the accelerators. And a little later on I'll talk about the software APIs that they use called ALF and DAX to manage the flow of work and the scheduling of work back and forth between the host and the accelerator, because we're looking at that too. This is a demo that was done by Mercury Computer Systems. They are using cell processors in some of their own products. And here what they're doing is they've taken a CAT scan. And a CAT scan consists of 2,000 to 3,000 two-dimensional images. And if you want to get a three-dimensional view of a medical image, you have to render each slice one at a time and then stack them up. So over here what you see is about every 2 seconds another slice is being added onto this image. This is using what's standard in the industry for this kind of work at the moment, an x86 server running a scalar program to render these slices. Somebody worked for 3 or 4 weeks at Mercury and took that same program, they SIMDized it and parallelized it to run on Cell, And now you get this incredible speed up, and you can view this three-dimensional image. So besides the fact that it's just faster, what this really enables a physician to do things in a very different way. So here, before maybe it would take them 6 minutes to look at an image, and now they can actually use this to compare against many images in a database. They can find out, for instance, if they have a patient that's got a tumor of a particular type, they can match it to other patients that have had that tumor, see how they were treated, what worked, what didn't work. And so this enables all kinds of new kinds of ways of working in whatever particular industry you can.
What
use
is
this
the
technology.
image? Where I'm trying to guess what the image is.
I think it's a spinal cord.
Hips?
Yeah. Now, in terms of what's hanging off of it,
like it has
it just looked kind of bloody to me, so I'm not quite sure what that is. Now this is another area that Cell's very good at, which is this interactive ray tracing capability, or this graphics manipulation. So here what we've done, what they did down in Austin, is they took a Lamborghini, and by the way, if you work at IBM for 5 years, you get a Lamborghini. So what they did is they took 7 blades. You see blades 0 through 6. Each blade, as I talked about, has 16 SPE cores, and they have some code that will essentially dynamically balance the work across these cores, so that in the upper left-hand corner, for instance, where there's almost no image data, one SPE has a big space, and where you have a lot of activity, an SPE has a smaller space. So you'll see this Lamborghini rotating in 360 degrees with various light sources coming in, and the bank of cell blades here will be doing a number of physics calculations to essentially calculate the light reflection. In some cases, the light will get sucked into the paint. Other times, it will get bounced out. As it goes through the windshield, you'll see it refracted a little bit or bounced off the mirror. So here you can take a look here. So again, try to focus in on the light reflection and what's going on. Now, of course, this is a little video that's on my laptop, but I've seen this real time, and it goes this quickly.
That's just like my Lamborghini.
Yeah.
Mine's a hybrid.
The hybrid Lamborghini.
All right. So now let me start to shift over to the Z part of the discussion. So there's a startup company in Brazil called Hoplong, on a very beautiful island off the coast of Brazil, so I'm told. And they have been designing and developing a massively multiplayer online game called Taekwondo. And in fact, they just went into production live about a month ago. And they've decided to run this massively multiplayer online game on a System Z system. And they're now in the process of incorporating cell processors into that production environment to do certain aspects of the processing. So this is a concept video, just to show you what they're doing. Now, some of the images here will be rendered on the user's workstation, but all the data that's being sent out, that's all being done on a System Z box. So actually, right now they're running this on a 4-way, 4 IFLs. And this is not the same. This is not IMS transactions right here. So what was interesting to me is I was in Germany. The Berblicken team in Germany, in the IBM lab in Germany, really has been the main focal points for this company to work on this. And I went out there. I was at a meeting, but I wanted to learn how to play this game. So we hooked up a joystick to a Z system, and I'm flying a spaceship around. And I can't stand the music. I'm flying the spaceship around, and I'm accumulating various. I'm accumulating Starbucks as I fly around, and I hit various waypoints. And after a while, I had a lot of Starbucks. And he said, "Well, you should go to the store. I forget what he called it, and buy some weapons or something like that and put them in your ship. And so we go to the store, and I see there's various kinds of laser guns and force shields and all kinds of things. And at the bottom, for only 15 Starbucks, I could buy a case of space beer. So I went to buy a case of space beer, and he said, whoa, whoa, don't just buy one case. You buy 500 or 1,000 cases, put them in your cargo bay, and when you fly to another galaxy, you can barter them or trade them, and or sell them. So, and that's when I became aware of really the commercial aspect of this environment, where they'll be doing virtual commerce, but they also will be doing real product placement. So at some point, it may be possible that I decide to buy a case of space beer, and the next day a case is delivered to my door. So their intent is really to expand this more high-performance computing kind of environment to really generating a lot of commercial activity. Really, you know, the Second Life kind of virtual world kinds of activity with real commercial business. So when IBM corporate got wind of this, they did a big press release about the game frame, and it caught a lot of attention. And at the time, I was just starting to look at Cell from the Z perspective. It was one of the things on my list of things to do. But we got so many inquiries that it's pretty much become my full-time job since then. The idea that you can now start to reintegrate HPC kinds of calculations back into a Z environment has really tapped a lot of real interest from some of our customers. So here's what was interesting to Hopple on about using System Z. So if you look at a massively multiplayer online game today, they configure the servers in what they call shards. So maybe 1,000 users will get onto a cluster of x86 boxes, and that'll be a shard. And then the 1,001st user will get put onto another cluster. And so if you want to play against a friend or whatever, and you end up in different shards, you really can't interact very easily together. And there's a lot of inefficiencies. You end up with the clusters of clusters, particularly as these larger games starts to grow with a lot of users. So they were interested again in the large shared resource pool concept, where each shard would become essentially a Taiko-DOM module running as a Linux guest image on top of ZVM. They're running DB2 on Linux, hypersockets over from the games over to the database, and now they're getting all the advantages of the large shared resource pool that I talked about before, and they can also do very easy and fast provisioning, particularly if a lot of users starts to log on to this, and they can now add an IFL at a time and not have to change anything else or readjust their users across shards and things like that. However, they also had this requirement to do high-performance computing, essentially physics simulations to do motion and collision detection. And they were saying, we can't do that efficiently on Z. So someone said, well, if we can do that on the Cell processor, that'd be ideal for Cell. And if we can manage a pool of Cell processors and simplify the management of that pool as an integrated part of System Z, then we can provide you the best of both worlds. You can get your HPC capabilities here, your large shared resource pool over here, and not have to give up all these things that you really wanted to have from an operational perspective just because you had some HPC requirements. So this topology and this concept now I've presented to a lot of commercial customers who aren't interested in playing games, although you can argue that that's what Wall Street's been doing. But maybe they're running trading applications over here on the left-hand side, and now maybe they want to do Monte Carlo simulations to figure out what the price of a stock might be 1 year from now or 5 minutes from now. Yeah.
I have a question, but how do you make sure that the I/O process between the two processors, I mean the C on this side and the Cell on the other hand, is not going to actually affect the performance that you can actually have on the Cell?
That's actually one of the biggest issues that we've been focused on. Let me get back to that in a few charts. I'm going to show you a demonstration in a few seconds, and then let me get back to it. And if I forget, re-ask the question.
Okay.
But the speed and the bandwidth and the latency on that interconnect is a critical component in making this work. Here's just some performance comparisons between, this is for the QS22 blade that has good double precision floating points. These are some Intel boxes compared to a cell box for various kinds of things. So HMMER is a medical imaging kind of calculation. These three here are financial services sector calculations, and there you see the CDOs right in the middle. And here's the comparison of Cell versus Intel, and you can look at these comparisons in more detail. I'll provide you with these decks, with this deck. So now let me move into really System Z and Cell and how we plan to kind of merge these technologies. This is a lot of times I'm presenting to customers who really aren't familiar with the mainframe, and this is kind of one chart that discusses the value of the mainframe. And we have some really modern tape drives there in the picture. And so I'll skip over that from now. So here I go back to this comparison of the potential scope of purpose with the efficiency of the task of these different kinds of processors. So the thinking might have been, well, a Z system is a general purpose processor on the far left, but we've done a little twist on that. So what we've said is that a System Z system is really a specialized system, and it specializes in transactional and database processing. And as I showed you before in the decisions we made, even how we designed the chip, we've made design trade-offs so that we specialize in virtualization, reliability, error recovery, and power efficiency. So we don't want to sacrifice that design point to do high-performance computing on System Z directly. Now over here you've got Cell, which we say specializes in computational stream processing, a 4-to-1 advantage in terms of over digital core sizes, again also very power efficient. And in the middle you've got your general purpose x86 systems. So on one hand they're saying, oh, we can compete with System Z, we can do virtualization, we can do all this stuff. Well, to do that they need to have more cache and fewer cores. At the same time we're saying we can do all the financial services high performance computing calculations on clusters of x86s. Well, to do that they want more cores and less cache. So they will either have to start coming out with multiple design points, or they're going to try to be a jack of all trades spanning the two and not specialize in either one of them. So what we're saying is, if we can do a good job of combining this technology that specializes over here with this technology that has a specialty here, then we can cover a full spectrum of computational requirements in this commercial HPC space. So that's kind of the philosophy that's driving us, or the thinking that's driving us. So here's a demo that we did. And so here's kind of a simple trading environment. You've got a trader over here with an Excel spreadsheet, and they're looking at a bunch of options, and they're saying, I'm thinking of doing something with these options, and they want to find out what's the price of these options, what are the price of these options going to be a year from now, or what's the probability they will be a certain price. And then they run these Monte Carlo simulations, which are these partial differential equations, and they drive them with random numbers to get kind of a curve of probabilities. And so, and in the middle now we put an application running on either Z-Linux or Z-OS. We've done it on both. And then over here we have a blade chassis, an IBM blade chassis with 2 cell blades in it, 2 QS22 blades. So we now have, between these 2 blades, we've got 32 SPEs, or we've essentially added in a way a 32-way high-performance computing capability to the Z-Box for about $20,000 worth of hardware. So here's the actual application that we ran. We kicked off, we have a Java application, a multi-threaded Java application. And in this demo I'm going to show you, we're going to run the Linux version. And we used JDBC to pull options data out of a DB2 ZOS table. So we've got a bunch of options in DB2. And then we send over parameters to the QS22 blades, cell blades over here, where we run these Monte Carlo simulations, and then we return the answers and commit them into the database. So I've got to jump out here and I'll start this up. And so here is the options in the database. We actually will pull 4,096 options out of this database. So you see the ticker symbol, the share price, the strike price, and these are variables like volatility percentage and yield percentage. And what we want to do we're running a European options calculation. So that basically what we're saying is, what's this going to be worth a year from now? And those answers will go into the payoff column. So this is just showing you a little close-up, and this is a video. We did this live down on Wall Street at the SIFMA conference and the High Performance Computing on Wall Street conference. Actually, at SIFMA we actually had the Z-Box and the cell systems right there. So now we were to run 6 batch jobs. Each job we're running is going to run 100,000 random number simulations against each option. And the first time we'll run it on one blade, one SPE running on one blade, then we'll do one SPE running on 2 blades, eventually up to 16 SPEs across 2 blades, or 32 SPEs altogether. And now this is the Excel spreadsheet. He's actually kicked off the job, and you're seeing the 6 batch job results come in. Again, 32 SPEs, 100,000 operations per option, 4,096 options altogether. And if you look at this on your own, you can see we've broken down the various parts of the response time, but basically I'll focus in on the overall elapsed time of the job. Oh, I think it expands in a second here. Well, let me just freeze it. So basically right here, this is the system Z elapsed time. So this is the job at a DB2 to sell back to job back into DB2. So the total elapsed time for the batch job. On one SPE, about 5.8 seconds. On the 32 SPEs, the whole thing's completed in half a second. So we're doing 4,096 options, 100,000 calculations per option in a half a second. And we're at a rate of about 1.35 billion operations, floating point operations per second. Yes?
It looks like that type of application is what we would call, perhaps, I suppose, embarrassingly parallel. Meaning,
yes.
You go out there, you compute, and you're done. It's not like interactive. Meaning where, latency is...
So I wanted to show you this so that I could get back to his question, which is the same as your question, I think.
Right.
Which is good questions.
Right.
So this is an environment we're probably showing off this marriage of technologies at its best.
Right.
In more of a batch type environment. And I would argue that's probably the best place for this. Now we are doing something with the customer where we have payments coming in where they want to do calculations on those payments real time on a payment at a time. And now the latency of that TCP/IP interaction over an Ethernet, we have a gigabit and now 10 gigabit Ethernet connection, is actually a little bit of a problem.
Yeah.
So we've been trying to convince them this particular customer didn't do a very good job of multi-threading their application. And we've also wanted to essentially multi-thread it in a way that we could take advantage of burstiness and activity. So if 2 requests came in at the same time, we send them both over together. If 4 requests came in at the same time, and that way we can amortize the cost of the internet connection. I'm sorry, the IP connection. So, of course, then the customer says, well, I now have to change some things in my application, and that becomes a little bit of an inhibitor. So those are kind of the experiences that we're dealing with. We've, you may have, Raj Krishnamurthy,
yes.
I think you met, he's actually done a lot of the really creative work on how we can minimize this latency and block the burstiness of these real-time transactions. So he's been doing a lot of work in trying to optimize that connection for these real-time interactions to minimize the latency. However, what we're also realizing is what we need to do is we really need to move to a faster connection. And so what I've been advocating is that we go to InfiniBand.
But now there is work on both sides, so you
Yep.
want to, in a way, try to convince the customer base that some kind of restructuring of the application has to happen so that applications can be as embarrassingly parallel as possible, I guess.
Right.
Because, you're
So-
going to have a limit of
So a
the
lot
time
of times
scale.
you talk to some customers and they go, oh, if it's anything more than to recompile, this is just too exotic, I can't do this.
Have the skills to do it.
Recompile, vectorize the whole thing for me, let me run, and otherwise we just can't do this. And my guess is a year or 2 from now, the customer's going to come back and saying, well, I'm used to getting this, your next box isn't so much faster as I expected, because you always gave me, 30 to 50% speed ups from each previous generation, and now I may not see that. And my competition now, that maybe has done some of this work, is doing more work in more real time, because they have looked at the subset of their application that they can SIMD-ize or parallelize or optimize using these concurrent techniques. So what we're saying is that sooner or later, customers, to maintain their competitiveness, will need to do this. And they're going to have, whether they do it on Cell or on Intel or NVIDIA, they're going to use a lot of the same programming techniques to do that. Yes?
Would instead of having the customer do that, would you be able to put a front end or a back end on the customer's machine to do that for them?
Well, you're getting into some stuff a little later in the presentation, but the whole area of programming models and the software ecosystem around this is a hot issue. So on one hand, there's been a lot of work to port libraries that have been optimized for Cell or were SIMD-ized, like the bullet libraries, I guess some of the sim libraries that you guys are working with, so that all you have to do in your application is call these libraries. They've already been optimized, and you don't have to do all that yourself. They've just started to support OpenMP, where you put a pragma statement above the piece of code that you think can be SIMD-ized or parallelized, and then the OpenMP compiler will handle some of that for you. But there will be times where you may have to go in and restructure a little bit or certain parts of your mainline application, and that may not always be easily automated. So there's the mainline part that's going to stay on the host, and how do you facilitate the optimized interconnect, and then there's the part that's going to run on Cell, and there's more and more tools that are coming out to do that. Now, if I can jump the gun here a little bit, well, you've got the idea, I think, of this. I think you got the main point of this. I was going to talk about scalability, but let me get out of this so I can get on to some of those other discussions. But I'm going to come back to the programming discussion in a few minutes, and we can stick on this if I don't get some of your thoughts. So today we have this, if you look at the top, we have a Z on the left, and in the middle we have the Cell blades, the QS20, 21s, 22s. And we have that Ethernet connection on the left. Tomorrow, and the date not yet public, we would like to move towards an an InfiniBand connection. And the big thing with InfiniBand, again, besides just the fact that it's very fast, low latency, and high bandwidth, is it has this remote direct memory access capability. So essentially what you can do with RDMA is you can point to an area in your host memory, like in the Z memory, and say, move a big chunk of data over to the Cell blade memory. You want to move it from here, you want it to there, and you don't go through the TCP IP stack or use up a lot of operating system cycles to do that. So you can move a lot of megabytes per second with much less of the operating system cycles being consumed to do that. So that's a big advantage of the InfiniBand capability.
So what type of latency are we talking about with this InfiniBand? Because we're looking with our Opencl simulators, in the tens of microseconds of latency, per collision detection operation. Mm-hmm. So what are we talking about with InfiniBand?
Well, I'm looking at numbers on other platforms where I'm seeing numbers that are down in the 10 microseconds and less for some of that. Now, once we put it into an end-to-end environment with Z in a Cell or whatever, I can't quite say what that latency will be, but basic pure send-receive of a piece of data with InfiniBand, I've seen those kinds of numbers. Now the other thing is, the larger the data, so if I take an example like that Lamborghini example, very likely we're passing 32K frames over, and now you have huge speed ups with InfiniBand if you use RDMA to move those bytes relative to Ethernet. Now there's a religious debate in the industry about Ethernet versus InfiniBand. Ethernet is moving to something called iWarp, where they'll also provide RDMA capability, and there are vendors out there doing some kind of RDMA on 10 gigabit Ethernet, and others are saying they may be able to do it, but they'll never be as fast as InfiniBand, that there's not as many InfiniBand suppliers. This is our Ethernet. People already have Ethernet backbones, and they don't have InfiniBand, and the debate goes on and on. But in the Wall Street area, there's an intense interest on as low as latency as possible, and a lot of them have invested in InfiniBand. These are the kinds of applications that we're looking for: a combination of mission-critical functionality, lots of data, transactional content, computationally intense operations, but again, where there's a need for governance like security, compliance, availability, reduced power and space, and basically all these industries have now some aspect of HPC computing in them. And so we're trying to, again, to marry these technologies and go after some of these. We focus so far mostly on the financial services sector, but we're not limited to that. So I talked about before the programming model that was used for the Los Alamos Roadrunner project, where they got 1.3 petaflops with an AMD host, an Opteron host, and a cell accelerator. So we're talking about using those same APIs called ALF and DAX between a ZOS or a Z-Linux host and the cell accelerator over here. So this was developed for Roadrunner, but it's a generalized platform generic host accelerator API. So the DAX layer is basically managing the data communications flow and the synchronization of the flow of data back and forth. The ALF layer above that is essentially providing work block scheduling back and forth to the SPE. So this is more of a scheduling kind of functionality, and this is more of the data communications functionality. And so our plan is to enhance the ALF framework. We've now got this working on Z-Linux and ZOS to incorporate some of the qualities of service that we get from ZOS, things like WLM performance, SMF accounting for chargeback, security and RACF integration. We'll be able to sense when a cell blade has failed and restart something on another cell blade, more virtualization than is currently provided. So we want to build in our qualities of service into ALF so that you can use this host accelerator API but still get some Z value. Now, very recently, we've been looking at an alternative to this, which is Opencl. Opencl is another host accelerator paradigm, or API, that's coming out of the Kronos open source group. And it was this activity was initiated by Apple. And they want to be able to plug GPUs into an Apple server. And they don't want to have to write an application that specifically is for an NVIDIA GPU or an ATI GPU. They would like to be able to write it once and run it on different GPU technologies. So in some ways it's got the same kinds of concepts as a JVM, or Java Virtual Machine. I've been calling it kind of an HPC virtual machine. So the idea is that you would have an Opencl runtime on your host over here, and you would write your application that would, and you would compile it to produce these generic HPC bytecodes. And then when you deploy it and run it on this accelerator, you'd have compilers that knew how to take those bytecodes and optimize them for the particular back-end architecture that's on the accelerator side. And so that gives developers a lot more flexibility. If I'm going to invest in changing my application, my mainline application, my accelerator part of my application, I don't want to be locked into only one vendor's hardware, because you might go out of business, or you might stop making something, or you might very dramatically change the way you make it, and I want to be able to not have to reinvest from scratch. So this Opencl spec was just approved last week, in 6 months since the founding of the group, and we're starting to look at it pretty closely, and we think this might really open the door to more and more applications being written to incorporate these technologies. Okay.
Almost out of time.
Oh.
About 4 or 5 minutes.
All right. So let me speed up here. I'm getting pretty close. So in terms of how we're looking to integrate this from a physical packaging perspective, is right now our plan is that we will have a rack of blade chassis in close proximity to System Z. And in these blade chassis, we will take any, I wouldn't say any, but we will take accelerators that are in the blade form factor and put them in blade chassis, and we're going to provide a number of capabilities to allow us to manage these blades as if they were part of the System Z environment. So in the case of cell blades, You'll be able to get onto the Z hardware management console, the ZHMC, essentially console that runs your Z system. You'll see, oh, I've got some IFLs, I've got some general purpose processors, zip zaps, and I've got 8 cell blades sitting out there. And I've got some data power plates sitting out there. You'll power them on, you'll load the firmware onto them, and then while you're running your application, you'll be able to monitor the health of these cell blades, and then over time, we will be adding capability from a management perspective in a partition running over here that will actually have an end-to-end view of the performance, of the application's performance across these two heterogeneous components. So this is a very active project right now in Poughkeepsie where we're going to be integrating these kinds of technologies. And the idea is that we're going to run cell blades as if they're extensions of System Z, rather than have now these cell blades being operated or managed by another organization within your company, independent of this organization that's doing the Z, managing the Z system. So
By any
because
chance, do you have like GA time frame?
not yet for this. Yep. I'm going to skip over the discussion on power consumption and how we reduce the floor space and power consumption operational complexity, and just get to the final chart here. So basically, you can see the potential, I think, of cell processors. I think you can see the potential of integrating high-performance computing into a commercial environment. And what we want to be able to do is to really do that in a holistic way, that you're able to really extend the Z qualities of service to this new architecture. And so this is really summarizes a lot of things that I've been talking about. And we're learning as we're going. But you know, when I talk to customers about this, they're very, very attracted in this kind of concept. This is, you know, the cell comes in many form factors. Sony PlayStation all by itself. The Roadrunner supercomputer is integrated with x86 technology and cell. There's not a lot going on with P and cell at the moment because they have their own vector capability with their VMX architecture, and then their System Z and cell for the kind of environments that I've been talking about there. So I'll just skip over to this one, and I'll be happy to answer any more questions. A bunch of charts in the back about the software ecosystem and the various libraries that run here and the development tools and so forth, and different options on how much do you want to optimize your program and how much effort you have to put in and so forth. But maybe that's for another discussion.
Thank you very much.